There we go. So we are trying to finish up chapter 4. Vacancies are very important in these materials. There's a lot of reasons behind that. There are a couple examples that we're going to take a look at. So one of them that they're using as a reference point here is a low energy electron microscope view of a 110 surface of nickel aluminum. And this is trying to get you an idea because of some of the charging effects and other things that happen in the SEM stuff that I think you guys will learn about later in the semester when you go to examine materials. There's a change. As the temperature changes, the surface island of atoms grow, and so you see what look like almost like rings or groups of atoms growing in different rings. It almost looks like a topography map or something like that. It's very similar to what actually happens, just at a molecular level instead of a macroscopic level, like mountains. So the equilibrium vacancy concentration increases because of the increased mobility of atoms from that higher kinetic energy. And that motion from where the crystal actually joins the island there. So the island grows and shrinks to maintain equilibrium vacancy concentration for the bulk. So it's showing you a side view here of what this looks like. And so the island, the ring that you see there, we'll see if it actually plays. It may or may not. So as the temperature decreases, that shrinks. As the temperature increases, the areas of the island increase in order to maintain this equilibrium set. So that's what's actually occurring in real time. So as the temperature decreases, the equilibrium concentration of vacancies drops and fewer atoms are in the upper island. So the atoms are migrating up and down as the along the, again, crystalline planes here, as the concentration changes as a result of temperature and the total kinetic energy in the system. So it's helpful to be able to kind of visualize that at some level and know that we're not just making stuff up because we can't see it and it's all too small. So the imperfections in metals are fairly important. So the solids, especially like solid solutions, are pretty important. Some of those result from substitutions. There's a combination of different atoms and they are randomly distributed. They can also be interstitial for a solid solution. So it's one kind of atom dissolved in another. That's the fundamentals of the idea here, is that something is dissolved in another species. The interstitials can be fairly straightforward for a number of reasons. Then you have, at a slightly larger scale, you can have a secondary phase within this group that has a different composition from the bulk around it. That relates often to a different kind of structure, and so this is part of how grains and grain boundaries are formed, or how new grain growth forms as temperature changes, and there can be a different particle arrangement in some of the examples that we've seen, because these atoms can change the orientation, and so these are all vertically oriented planes in what would otherwise be a diagonal matrix surrounding them, or a hexagonal matrix surrounding them. These might be a small block of body-centered cubic groups. And so you might have a crystal body-centered cubic in the middle of what would otherwise be a hexagonal pattern, for instance. This can be fairly common in solid solutions because the atoms are often of slightly different size, and that creates some of those voids and vacancies that especially allow for some of the large-scale material behaviors that we actually see. So it's important to understand how those function and how they operate. So the imperfections, the conditions for these specific kinds of imperfections can be helpful to see. So in order for a solid solution to exist, there's a Hume-Rothery rule, which helps to give kind of some guidelines. So if the atomic radius, the difference specifically, so the delta R, the difference in atomic radius for these components is less than 15%, that creates the circumstances that you need in order for this to exist. So the atomic radius needs to be, the difference needs to be less than about 15%. The proximity in the periodic table, they need to have similar electronegativities. So these are things that you're going to see in the periodic table when you go to take a look at those, especially when you're trying to reference them for a test to make sure, does this make sense? The same crystal structures are going to exist for pure metals as for the solid solution. So they're not going to suddenly become body-centered cubic from face-centered cubic because it's a solid solution. So the crystal structure of the pure metal stays the same as what it was. And the valency, there's a kind of a key parameter here. All else being equal, meaning we're going to isolate this one aspect, a metal is going to have a greater tendency to dissolve a metal of a higher valency rather than one of a lower valency. The reason for that is kind of there's several aspects to that. But the main important one is just to know that the metal is likely to dissolve a metal of a higher valency rather than one of a lower valency. The ready available cloud of electrons is a part of that driving factor. There's a couple other things that can contribute as well, but the keys really here are all else being equal, these have these higher valency atoms are going to be easier for a material to absorb. This is part of why something like metals tend to have some small amount of atom migration, not necessarily in the case of when something like a bolt is left torqued in a specific location and it's left there for many, many years. There can be a difference in how that gets taken loose. If it's a bolt that's just been in place for a couple of years, it's usually fairly easy to get it to break loose. If there's a large dissimilarity between the valence state of the metal atoms on either side, you can actually have a solid solution situation happen where at the macro scale, it's often called like it's called like a friction weld or a fusion weld, sometimes kind of incorrectly, but it's a slow transfer of material through diffusion over time of those metals, and you actually get a difference in size. You get a physical size change in the metals as a result, and that creates a much higher breakaway torque. situation, particularly if something is a mild steel going into a cast iron or something, and there's a big difference, plus a small amount of corrosion or oxidation in between those layers. All of that can contribute to creating a metal migration that fuses the surface. So the fusion weld term there is a little bit more accurate. But it's not the same thing as doing a fusion weld like you would do with a TIG welder, which again, you guys will learn about a little bit later. So these imperfections and kind of applying some of these rules to solids, we want to think about, would you predict more aluminum or silver to dissolve in zinc, based on what we've seen there? So the atomic radii for aluminum, let's make sure to mark those so that we are familiar with what we're aiming for here. So aluminum or silver to dissolve zinc. So first thing is, let's see a vote in the chat. Which one is going to be more likely to be dissolved in zinc? So these are higher in valence, or one is higher in valence, one is lower in valence. So it's important to know. Electronegativity is sort of similar between them all, so that's less of an issue. But which of these two? Let's see a vote in the chat. See a vote in the chat. Which of these two, based on what you know? Okay, I see some votes for both. Not quite an even split. So why aluminum or why silver? I see a lot of silver. That seems to be the popular choice. Few of you have recognized it's a trap, so voting is futile because there's a lesson to be learned. But it's important that you still participate for a variety of reasons. So why aluminum or why silver? Yes. So the biggest difference, both of those values, as far as atomic radii, are less than 15% different, right? They're both within less than 10% different. So the main deciding factor then is the valence state. A lower valence state is much less likely to be absorbed, and that's part of the reason why you're not going to find the same degree of silver in alloys as you will aluminum. So aluminum, chromium, those are higher valence states. That's something you're much more likely to see. So something like iron and chromium to make stainless steel makes sense. Iron being 2 valence and chromium being a 3 valence, and their atomic radii are very close, right? So very important to understand those aspects. Another one is, and we'll clear these. So for zinc and aluminum, same deal. So zinc and aluminum into copper. So copper is 0.1278. So zinc or aluminum. So there again, you have to ask a couple fundamental questions. Let's see the votes in the chat based on what you know. Are we more likely to see more zinc or aluminum in the copper? And why? A lot of people saying zinc into copper. What's the main reason why? Both are within that 15%, so you can't disqualify one based on the atomic radius. But that is why, for instance, you're not going to see hydrogen or oxygen in there. So close. This is where the so the copper and aluminum are actually only about 12% different, because you're comparing with copper as the base. So it's 1431 divided by 1278, gives you 1.119, which is about 12% difference. So aluminum is 12% more. Zinc is even closer. So 1332 divided by 1278 as your base. That's only about 4% different. So both are still within the 15%. So the 15% is the criteria that would discount hydrogen and oxygen or carbon as solid solution. Because if you were to do carbon and iron, those are quite a bit different in size. So that might get you outside that 15% ratio, but it's not the it's the difference between them, and that's the big factor. So really, the only thing that you have to go on there is the valence state. So aluminum is a higher valence state. Zinc is the same valence state. So you're definitely going to have aluminum there, but you could make a reasonable argument for both. You're just going to have more of aluminum, and that's why that's actually the correct answer for this. So that's the key there, because you can look at the electronegativities as well. Copper is a little more electronegative than the other two, but the aluminum being a higher valence is going, and still within the same size, is going to be more attractive statistically than the zinc. And that's the reasoning why. All right. So one of the things that we need to understand is weight percents. This becomes very important as we go to deal with mass fractions in these components. So these mass fractions are very important because it gives us a ratio that will allow us to understand what the weight percent of something is. This is what's going to enable us to understand what's going on with a couple different components, including the carbon content for a given iron material and things like that. We can also calculate the atom percent, and in either case, you're using the same concept. So the mass of one divided by the sum of the masses times 100% to convert from a fraction to a percent. That gives us the mass fraction or the weight percent of component one. This is one relative to the total, so this is something that should make sense to you guys. I shouldn't have to explain why that works the way that it does. The atom percent is not always going to be the same because of the relative atomic masses of different things. So you can specify either by atom percent or by weight percent, and that will change the calculation. So number of moles of component one is this NM1 that they're using here. There can be more than two, and that's another important factor. Most of the time, when we're dealing with a phase diagram, it's going to be two components. So in the case of iron, where we're going to camp out for a long time, you're going to have iron and carbon, and that's what's going to be your M1 and M2. There are other things that can be added in that change the phase diagram, but iron and carbon are the primary baseline for steels, and that's why we're going to study those to the extent we will. Line defects, you've seen some examples and demonstrations of those that make it a whole lot easier to actually visualize. So dislocations are line defects. There is a slip between these crystal planes that result when a dislocation happens. And we've had some more fun connection related issues there. So there's a lot of pieces to the puzzle. So these parts, especially like the example of zinc that they're using for this, it's important to understand how that's going to work. So we're going to do a couple of things to understand how this works mechanically. Some of that is going to involve the tension testing that we're going to do in samples, and you're actually going to get to see these slip steps take place. So as the metals are elongated, these planes slip against each other, and through the mechanisms that we've already seen, especially for something like zinc that is fundamentally hexagonal, there's a straight stack of planes. After the elongation, there's all of these slip steps, and you'll see what that kind of looks like. It's a very interesting phenomena. The linear defects are another type that you'll see. So this is one-dimensional, and it's around any atoms that are misaligned. So again, you've seen like the rug illustration of this. The edge dislocation, that's sometimes referred to as an extra half plane of atoms inserted into a crystal. It's always perpendicular to the dislocation line. There is also the screw type dislocation. So it's a spiral planar ramp resulting from shear deformation. B in that case is parallel to the dislocation lines. And that's B is referring to the Berger's vector, which is a measure of lattice distortion. So the lattice is being distorted in a spiral within a plane in the screw dislocation, whereas in the edge dislocation, it's perpendicular to that dislocation line. So it's applying pressure perpendicularly to the crystal structure. So we've seen some examples of what that looks like in practice. Those visualizations really help to make this concept a little bit more clear. So we're going to look at some more details for some examples of these. So the Berger's vector is showing you the direction of this distortion by having this extra set of half planes inserted here. And this vector is showing you where, sort of what direction the distortion is in. So down here, a few atoms away, everything is fine and normal at the base. But these bonds are all stressed in this region, and these bonds are stressed as well. Most of the rest of them are okay, but all of the bonds that are circled, these guys are too, as a matter of fact. So it's at least a couple of atom layers before the bonds return to normal and are not stressed. So these stressed bonds take less energy to hop from here to here to now, oh, we're going to connect here to here and move this dislocation, move this edge dislocation this direction. And that's what the Berger's vector is trying to show you, is this is the direction it's going to move as that edge dislocation moves. So instead of having to shift and break all of the bonds all at the same time, you only have to break and disrupt a row at a time, as wide as that is. A screw dislocation is a little bit different. So the Berger's vector here is along this direction. So it's trying to get you to understand how the material is shearing. So the bonds, instead of being attached along this line, the bonds are now, the lines have broken, and now it is dislocated. And this whole plane is now dislocated, and it's rhomboidal in shape at the location of the distortion. So all of the bonds in that region, all of them are under stress. And that means it's easier for them to be broken. This is part of why bolts shear in a sort of circular pattern, very typically, with some small sharp piece sticking up off the edge. This is physically what's happening at the crystalline scale. Is you have a shearing force from this rotation, and that rotation is typically, for this kind, it's in this direction. So you have a rotation, except the base is trying to be counter-rotated, and that's what creates this slip plane across the center where this dislocation happens. So this is trying to get a better understanding or a better view of where some of the atoms shift and those bonds shift. But instead of a plane of atoms being inserted in between, facilitating this, it's a smaller number of localized atoms. So you're not breaking all of the bonds at the same time. But this is often something that happens very suddenly. So it's not something that's super duper obvious. And they have in the visualizer for the text, they have an example of what this looks like. So everything sort of shifts over one bond number in this group, but then you don't have a direct bond of all of the atoms exactly anymore in layers. At that interface, the bonds have all been weakened by this process. So there's not a direct atom to atom bonding the same way that there is in other lattices. So this is something that can be helpful in order to look over and understand kind of what's going on there, to make sure it makes some sense. There can be a mixture of dislocations, which is also likely. So in the event of something like this happening, they have a half plane of atoms inserted here in combination with a couple other faults, and it shows you with the dotted lines this distorted region of bonds and where the Berger vectors are. So it's always in this direction. And even here, because it's perpendicular to the actual half plane of atoms, you have continuous Berger vectors, so they all can work together to create this kind of a defect in the material. This is not something that you're going to be able to see at the macro scale, certainly not with your eyes, but this is an example of a combination of dislocations all working together for a common factor. So there's a lot of pieces to the puzzle here, but you can have a few of these operating together, and because the Berger vectors are the same direction, it's fairly straightforward for the fault to form in this particular way. So you have the edge dislocation, you have the screw dislocation, and you have the mixture as the two sort of run into each other. Because the pattern doesn't continue, right here is where the pattern changes, and it becomes primarily an edge dislocation. The screw dislocation sort of terminates here, and the edge dislocation takes over as the predominant issue there. These are something that are very highly visible in electron micrographs. So under SEM, it's a lot easier to see these, especially if you've got if your sample is not just charging very highly, that can be a big issue. So the imperfections are going to be highly visible. Where you guys are going to see this the most is going to be when the close packed structures, we apply a bunch of force, we start to create these slip planes, and in the tensile direction, magnesium and aluminum are different here in their behavior. This has a very sharp diagonal dislocation. This forms almost more of a cup and cone fracture rather than being a diagonal failure point. I'm going to include another part of a video that's going to be, I think, very, very helpful to help clarify what the behavior looks like at the macro scale in a process. When you go to work on a material like this, when you go to do something with it, what does that look like? So the close packed planes and directions, for something like HCP, for instance, is going to behave differently. There's one plane, there's three different directions. The FCC, there's many planes and many directions for close packing. And so it can be a little hard to visualize, well, what does it mean to have these atoms arranged in such a way, if they're packed, especially in FCC, it's really hard to tell what crystalline planes are going to show up. There's a reason why multiple different planar structures show up for something like an FCC metal. And I think you guys will see that when we do the experiment for XRD. And then for BCC, there really are not the same planes with multiple directions. There's kind of one plane type and it's all uniform. So there's not multiple different directions that they're going. The hexagonal, you have planes going this way. You have planes going this way. You have planes going this way. So there's at least three, and that's what they mean by three directions, even though there's 6 arrows. Each of those is an infinitely long plane at this layer. But the next layer doesn't have that. The next layer is here and here and here. So it's still 3 directions, but it's trying to get you guys to understand what's going on with these. So these are specimens that were tensile tested. Aluminum, being FCC, has many different planar directions, and that's why it's able to form that cup and cone. Magnesium, which is hexagonal close packing, is always going to behave, the fractures are always going to be diagonal. And that's a thing that you can't avoid. So there can also be a twinning plane or a twinning boundary that can happen where there's a distortion, something is missing, and the crystalline lattice basically just takes a sharp turn, and there is a mirror plane for these atoms. So it's a reflection of atoms across a twinning plane. A twinning plane is what that boundary is. So there are some examples of those in real materials. For face-centered cubic, there are stacking faults that can happen. So it's no longer ABC, ABC packing sequence. It could be ABC, AB, ABC. And those stacking faults are a little bit different. So the kinds of defects that you can find a vacancy, you can find a kink or a crevice, you can find a ledge, you can find a terrace, you can find an atom, which is just a random piece that's sticking up by itself, like shown here. You can find a terrace, so a flat spot. You can find a step that's in between a couple things. So you've got a step. You might actually have 2 there. It's a little hard to tell. You have a ledge. So all of these things are things that you can really see, and a catalyst often increase the rates of a chemical reaction without being consumed. Some of that is because of these kinds of imperfections, for instance, is very common. So these are active sites on, in this case, they're talking about a catalytic converter for an automotive application. So it's a finely grown crystal that, you know, some guys go in there with a hammer and a screwdriver and cruelly break out their catalytic converter material that somebody very carefully grown from a little tiny seed crystal into a very fine uniform structure. These guys bash these things out in order to make their Chevy sound even worse than it did beforehand. So it's a thing, specifically among like Camaro owners, it seems like. So microscopic examination gives you some concept of what this looks like. These grains that are sometimes also referred to as crystallites, although I'll probably never use that term again. The grains and grain boundaries vary in size. They can be quite large. So you've seen examples of those. So we're not going to spend a ton of time on this. But a large single crystal of quartz or diamond or silicon, those silicon wafers are grown from or are cut from a very, very, very large single crystal of silicon that's grown very carefully under very tightly controlled conditions. Aluminum light post or a garbage can or something, you can see the individual grains sometimes, because they'll be very large and very non-uniform. Same thing with zinc coated materials. Zinc grains can tend to be very, very large. So the crystallites or the grains are going to be very small, usually less than a millimeter. And that means it's requires a microscope to be able to see. So what you're seeing is these different surfaces that are reflecting or refracting light differently, as the case may be. And the degree of polishing and etching on the surface does all sorts of interesting things with the light. So there's different scattering that goes on. And optical microscopy up to about 2000 magnification is useful. Sometimes to get to 2000 magnification, you're almost making surface contact directly. So it can be pretty tricky, but 1000x magnification is pretty straightforward and easy to use. But this gives you an idea of a few different crystalline orientations of the same material with these grains. And this is a top view of these three-dimensional grains, and they are in fact three-dimensional. This is an example of brass, which is a combination of copper and zinc primarily. So the etching and all of the polishing on the surface, everything gets ground. There's still a lot of minor imperfections in the surface that would be easier to see under electron microscope than optical, but that's what gives you the sharp color contrast in these materials. So grain boundaries are imperfections. They're more susceptible to etching. They can come up as very dark lines because more of the material has been removed chemically by the process. So those grain boundaries are where it's easier to physically knock atoms out of that location. So there really aren't exactly dark lines like that existing. Those are an artifact of kind of the process that we have to use to be able to see them. It's a little tricky. But the changes in the crystal orientation across that boundary creates some of the differences in how light is refracted or reflected across that boundary. So the number of grains in the group, this is something that you guys are going to need for one of the labs, as a matter of fact. So it's a formula you really want to write down. Is the number of grains per square inch at 100x magnification. That corresponds with 2 to the n, meaning grain size number for ASTM grain size, minus 1. So that's a formula that you guys are going to use when counting grains later in the semester using the microscopes. It's also important to know that the metallographic scopes are using polarized light in order to increase contrast. So they put a filter into place to only allow light with a common polarization pattern to pass through. And they're also useful for transparent samples such as polymers, in order to make sure that you're not seeing things that are basically optical tricks played by different levels of refraction by different orientations of the light that's hitting. So different degrees of polarization, different rotational degrees. There's all sorts of things. A lot of characterization techniques rely on precisely tuning those interactions. So the optical resolution is about 10 to the minus 7 meters is 0.1 microns. That's 100 nanometers. So that's just a equivalent. You can get to something like 100 nanometer feature size with optical, kind of, sort of. That's your upper threshold. For high resolution, you have to use something like X-rays, which are difficult to focus. The XRD, the X-ray diffractometer that we have, does a similar process. Instead of putting a physical filter, they have an actual slit that collimates the X-rays in primarily a bulk orientation instead of all different rotational degrees and things. It's a simple method of just blocking and reflecting things that don't come out in the correct rotational pattern for polarization. The wavelengths are for electrons on the order of about 3 picometers, which is very, 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 very small. That means that the theoretical max is about a million times magnification. I can tell you, having done a lot of work down around about 300 to 330,000 times magnification. If on the same, within the same square mile that you're in, there is a heavy truck driving on the road, the amount of vibration that's transferred through the earth from the truck to the machine, let alone people just walking in the building, which creates distortions in these kinds of SEM images. It's not reasonable to tell everybody in the entire building to just stop walking. But even so much as a truck driving within the same square mile of solid ground as where the site is can create distortions around 300,000 magnification. And it can be plus or minus about 5 nanometers in resolution. So well below or well above the resolution that the electron microscope can do. However, your clarity of image and quality of data is inversely proportional to the actual limitations of the wavelength. At a million times magnification, it's very, very hard. You're getting very few electrons actually coming back to the detector. So it's very, very tricky to resolve up above really about 300,000 unless you're in a specialized facility, in a vibration isolation chamber, and the machine is mounted for vibration isolation, and you're not breathing extra heavily and all of those sorts of things. You basically have to be holding your breath entirely for many minutes at a time to be able to get images at a million X resolution. So you can get atomic resolution, but a lot of the images that you'll see of those are very, very blurry. So the electronic beam is focused by magnetic lenses, and those are very tricky to operate at those extremely fine extremely fine resolution. So there are some images here that have been colorized uh, in order to make them interesting, but there's a scanning tunneling microscope that can do imaging. So there's a person here made up of carbon monoxide molecules arranged on a platinum surface with a 111 orientation, and then iron atoms arranged on a copper surface that are meant to represent the term atom. So this is stuff that um, has existed, but it's very fine controlled work. So point line and area defects are things that exist in solids. They're fairly common. In fact, they're unavoidable entirely for a lot of reasons. Um, the uh, the defects in the property boundaries and the grain boundaries are important for being able to control crystal slip, especially when you get a plane. It can only slip so far until it runs into a grain boundary, and then it can't continue to slip because that plane doesn't continue to exist. So that rug ripple running along the surface reaches the end of the rug, and there's no more rug, so there's no more ripple to go anywhere. And that's the most simple, most brilliant summary that I've seen. That's why I shared it with you guys. Defects, depending on what it is, can be desirable or undesirable because of plastic versus elastic deformation and things that we're going to learn about as we get into more depth with the stress strain curve and all of the other stuff that you guys are going to need to understand. So, no, discard all the ink notations. All right. So there's a couple things that we're trying to wrap up. We're just about out of time for today anyway. So as I'm pulling up this other example, questions. The magnesium one, here we go. That's the one I'm looking for. This is one that's going to really help clarify a couple of the last kind of key pieces of this relationship. And you guys will now actually understand something that these guys don't understand. Yes, you will have exam next week. I'm going to have to do it on Wednesday because reasons rather than on Friday. So you guys will need to be physically in person in class. The exam itself will be online. More details about that will come out. I will work on getting the equation sheet for you guys to be available. There's really not going to be as many equations as you think, but this will at least get us a starting point. The simplest explanation, the atomic radius is not the atomic radius itself, it's the difference between the atomic radius. So yes, chapters 1 to 3. The scientific calculator is fine. I know there's a bunch of people that are afraid you're going to program all the answers into it. Look, if you guys put in all of the time and effort to physically program all of your textbook into your calculator, then the thing that you've done is studied and learned 2 things instead of just 1. So that's a win for me. So you're cheating in reverse by half, and actually you've just learned the thing. So what you've inadvertently done is you've studied. So I don't care. the key concept there is you're not going to be doing things like on phones and texting. That's the key concept there. The radius is the difference between the two radii. So the actual mathematical expression there, I'll go ahead and write it on this slide and then show it to you. Because that'll be a little bit simpler. So delta R is equal to the radius of atom 1 minus the radius of atom 2 divided by the radius atom 1 times 100%. So this is the actual formula. If you need to physically see a formula, assuming it can actually correctly share, there we go. So it's actually the delta R, the difference in radius. The difference in radius is the radius of atom 1 minus the radius of atom 2 divided by radius of atom 1. Depending on which one it is, if you get a negative value or a positive value, it doesn't matter. You could also simplify this out to simply dividing the ratio of one relative to the other. So if you're looking at nickel dissolved into copper, copper is the one that goes on the bottom. That's your relative to. So the ratio of the two will give you something like a, you'll get something like a 1.1937. That means 1.19 is 119%, meaning 19% greater than or less than if it's negative, 19% less than. That is greater than that 15% delta R that we're referring to. All right. So yes, that will be open note. The open note thing typically won't help you all that much. The exam, yes, you'll be given anything like electronegativities or things that you need to reference. That will be a thing.
Is a very exciting day because we have this solid bar of magnesium to play with. It's a metal that I've never experimented with, and I want to find out, among other things, can you forge this crazy light material? First impressions visually are, of course, that it is a grey metal that's picked up a little bit of an oxide.
What do you mean it's a grey metal? What metal isn't grey?
What would you say if you looked at this bar of steel? You would say, wow, that's a shiny metal. Grey.
Shiny grey.
Shiny. This is aluminium, and much like aluminium, it picks up a surface oxide here at room temperature, making it look that little bit dull. But of course, the most pressing thing about magnesium is how crazy light it is. Really, I should say how little density it has. This whole bar only weighs 1.28 kilos, 2.8 pounds. And if I pick up an identically sized bit of steel, you'll see the steel is 4.5 times heavier, 5.6 kilos, 12.3 pounds. And so because we have a block of tungsten from trying to forge it, we now have some really weird mind games that we can play. Come on, Jamie, pick up the magnesium.
Whoa, it's so light. It's kind of like a baton that you'd use in like a running relay.
It's that light, it's kind of crazy. If I wanted a bit of steel that weighed the same as this, it would look that big. And when you cut off a short little section of magnesium, it basically might as well be a baseball or a cricket ball. It is so light. Catch that, Jamie. Look at that. Hilarious. We've got two different alloys of magnesium, Electron WE54 and ZK60A. So we can see if there are any differences. For now, let's start with the hand tools. What can we do with it?
I'm assuming it's dead soft, right?
I think so. Just kind of like holding it and moving it around and listening to it. I think it's going to be quite comparable to a block of aluminium.
I mean, there must be a correlation between the density of something and how hard it can be, surely.
I am not a scientist, but I don't think it's necessarily the case.
But you would think that because of the atoms that make something dense, something light has less atoms and therefore is easier to cut, there's less to move.
Maybe. We will have to find out in the comments below because neither of us are scientists. Here's the chainsaw file. Oh yeah. Plenty soft. Made a good little effect there in no time. Let's compare that to aluminium. I will actually say that aluminium is getting bit more by the file. Feels like we're taking off more material than on the magnesium. Let's try the other alloy. That feels identical. My verdict on filing is that the two alloys of magnesium are nearly identical, but they are both just a little bit harder to cut than the aluminium. Now, if we break out a hacksaw, very easy to cut with a hacksaw still. But one of the things that I think is quite cool about aluminium is aluminium can be cut with wood tools.
The Republicans have an agenda to get rid of abortion in America.
Mitch McConnell and the MAGA Republicans are the ones who recruited Nella Domenici.
Why is she coming to this state? And also, why is she backed by these people?
A vote for Nella is a vote for a national abortion ban.
World, the time has come to push the button. World,
This is a wood panel saw, making a pretty good effort at cutting this aluminium bar. Question is, can a wood saw also cut magnesium? Look at that! That is a discount and 4 additional months for free. Check them out below. Let's get back to it. Well, it definitely melts. I wonder if it needs more amperage. That was 116 amps. Let's see what happens if we send it. Oh, yeah. Wow! Holy crap! Delightful mess. You can definitely make a puddle out of magnesium without it catching fire with the TIG welder. Next up, malleability. How about when it's cold?
Damn, that was loud.
Ah! Ooh, interesting though. Look, a crack is starting to form around where it had some little TIG weld puddling. Oh. We got a break. Wow, very interesting. So its malleability when cold isn't super good because though it's fairly soft, it does like to break. Cold under a 25-ton hydraulic press.
Note very carefully how it actually breaks and what the orientation is. He will not know the answer, but you guys do now.
Whoa! That's terrifying! Wow! Whoa! It's just so interesting to look at how that breaks. I've never seen anything break like that. The thing it broke off is so shiny. Now into the 80-kilo power hammer. Whoa! Magnesium is a high-performance metal. It's used in like racing cars and stuff now. One of its first industrial uses was World War I and World War II in aeroplanes. The Germans actually used a lot of it, and check this out. They called the alloy Electron with a K, and Electron is still one of the names that they use for magnesium alloy. And despite its industrial uses and high-performance uses, we see that it has limitations. So you can't have it all. You can't have a metal that's ultra super duper light and ultra super duper strong or ultra super duper malleable. There's just nothing quite like steel. I think we all know what our favorite metal is.
Metallica.
That's your favorite metal?
Yeah, maybe Deftones.
Interesting. It is now time to heat it up and forge it and see if it is any different. So this gas forge gets up to 1300 degrees Celsius, which is about 3 times as much as is required to set magnesium on fire. So of course we don't want to do that. Google says 290 to 400 degrees Celsius is somewhere about the forging range of magnesium, and considering the risk of burning down this entire business park, I think it would be prudent to stick within that range. And look at this. alive from the dead. I have had this kiln, this beautiful Paragon heat treating oven, sitting under the steel rack for 4 years. And finally got somebody in to get it.
Change of views.
Yeah, it was just hard. That is not what I expected. I expected this to feel like aluminium. I should show you what aluminium looks like. Here's a trick for working out if aluminium's hot enough to forge. Take a bit of wood, not hot enough to forge. You'll see what I mean when it is. There we go, that tells you it's hot enough to forge when it chars. Forging aluminium is kind of like this. You can hear how it sounds. It just sounds soft. It doesn't bounce around on the anvil and it deforms really, really nicely. So I expected, I don't know, because in my simple brain, magnesium, aluminium, the end of the word is the same. They have a similar visual appearance, and they're both quite light metals. For whatever reason, I thought they'd forge similarly. Back to the magnesium, it feels barely any different to how it felt when it was room temperature. So if I can't hit it with a hammer and make it deform, let's try it with the press at the same 350 degrees Celsius. Nothing. What? 25 tons of force isn't doing a lick of anything to it. What if I hit an edge again? Oh! Fractured it again. Damn! Looks like somebody with an enormous set of teeth has just taken a bite out of it. Let's bump that temperature. Let's get it to 400. She's hot. Let's try the power hammer. Oh, it's better. That's better than it's been. It forged! I would call that forging. Oh! We got just the slightest rhombus and it instantly ripped it apart. Wow! Straight down the diagonal. Get some! That is a work of art. Where's my touch mark? That is one bloody temperamental material. It's possible that it was getting too cold, but what I definitely know is that we went from a nice square cross-section to a rhombus, and it only took a few blows from there for it to rip. So it could be a combination of it cooling down too much and the rhombus, or it could be just the rhombus, but that's really temperamental. What I want to do now is try the other alloy that we have. It's this stuff right here, ZK60A. Our previous alloy, WE54, is called a casting alloy of magnesium. According to the internet, it is weldable by TIG welding, and it maintains a lot of its strength up to 300 degrees Celsius, so it's pretty good in a higher temperature type of situation, as compared to the ZK60A, which is described as being strong to 150 degrees Celsius, is not weldable, and is called a wrought alloy of magnesium. Casting alloy, wrought alloy. Something tells me that we're gonna have a better chance of success with this. Here we go. With the hand hammer. Still feels pretty hard. Way harder than the aluminium. It's gotta go to the press. I had so much hope. It says wrought in the name.
Carjackings rampant in New Mexico.
Gabe Vasquez's answer: cut punishments for carjackings.
It's not just about defunding the police, it's about defunding a system.
Gabe Vasquez, easy on criminals, hard on the police. The NRCC is responsible for the content of this advertising.
I mean, it's better. I think it's better. It hasn't split apart yet. I think it's better. I want to try upsetting it. Nothing. No way. It's just very hard. This at forging temperatures is even harder than steel at forging temperatures. I mean, obviously, it's a much lower actual temperature, but still very surprising. There we go. That's good. Much better. I see! Oh, I think we have spawned another crack. That's no good. Oh, look at that. That's a very unique break. Just ripped apart in the very center of the bar. Again on the diagonal relative to the square. It clearly has a very narrow forging window. And clearly it is ridiculously temperamental in that it fractures and rips apart very easily. We could forge on it for longer if we preheated the dyes, that's for sure. Another thing I know for certain is that I never want anything to do with magnesium ever again. I think this is just a sucky material. Option 1, it burns down your workshop. Option 2, it breaks apart when you try to forge it. The only saving grace it has is its really remarkable machining characteristics. You can take off material really well on the lathe and the milling machine.
What if you really need a poo?
And that sums it up perfectly. If you need to loosen up your stools, maybe you need a little bit of magnesium too. At least that's what the internet says. Let us know in the comments down below what metals you want us to try forging.
So, political ads notwithstanding, that gives you at least a frame of reference for why it is. So as we close out for today, let us know in the comments why it is that the metal kept breaking on the diagonal. What was the key feature that you learned about today that explains what the material behavior was? There's one key feature. Bueller? Nope. Everyone's looking dumbfounded. The hexagonal close packing arrangement. The HCP structure of magnesium is why it fractures along those slip planes that are always diagonal. So now you know what he doesn't know. And no matter how much he could manage the temperature, the slip planes that form in that specific metal, because it doesn't change crystalline structure at at those temperatures, it remains HCP. No matter what you do to the material, it's not going to forge correctly. It's always going to break along those same diagonals. So interesting things in the real world with the materials. All right. I will see you guys Wednesday.
Sure. So at the point where you've reached that critical temperature and you've, become a forgeable, like at temperature, right? Like steel becomes non-magnetic. Is that going to change the, like from FCC to body centered or?
So in some metals, yes, but not for magnesium specifically. Even in the other alloy, there wasn't enough of an alloying element to be able to change its structure away from HCP. So steel will recrystallize into a more malleable BCC depending on what the specific temperature is, and that's usually the range. Is they're getting away from any kind of FCC structure to BCC, and that's what leaves us. That's what leaves us the values that we've got there. So the HCP is what causes that particular planar fracturing in the magnesium.
Okay. And then for the test, if we can, do the homeworks without any problem, you think we're set?
You're probably on the right track, because there's going to be some concept questions, some written problems. I'm going to make some modifications to the test before we issue it, but I won't have everything finalized probably until late Monday, if I were to guess. So
okay.
I won't have answers for questions beforehand over the weekend. That I know for sure.
Okay. Will there be any like basic chemistry on it?
There will be probably some, so that we've assessed that, but there won't be like 100 like Chem 2 questions or something like that.
Okay, thank you.
All right. I will see the rest of you on Wednesday.
Professor?
Yep.
I have a question after everyone
Okay.
leaves.
All right. Any other final questions from the rest?
I had a question on the homework, but I don't know if they want to go first.
I'll wait. No worries.
Okay. Nicholas, do you want to? I don't know if he has a question. Okay. Professor, I'm gonna share my screen. Is that okay?
Yeah, that's fine.
Okay. I always forget how to do this on these. And then, do you end up uploading the lecture from last class? Because I didn't see it right away. I don't know if maybe I was blind. But...
I don't think that one's gotten uploaded yet. There's been too many. There's been too many things going on the last couple days. I was trying to get some things uploaded yesterday, and I don't think I got to that one. Or no, the one from the 25th. I think the one from the 25th should be posted, but I'll have to go back and look.
Okay, I'll check. I just like I think I've mentioned I like you reviewing them over. Do you see the question on your screen?
Yeah.
Okay, so for this question, I got the first part right. For this part, it was a little confusing for me, but it's saying the head, and we're looking at direction B.
Mm-hmm.
So it's
B,
not.
Yeah, B is on that on that
On the exact.
let's see.
Well, no, because it's looking at what.
Yeah, it's so what that's doing is that head is pointing to the front face at y equals 1. So it's half in x, half in z, 1 in y.
Oh, 1 in y. Okay, so it's because I answered this twice, but I don't remember what my first answer was.
Yeah.
Wait.
So it might be misaligned with which
yeah,
A in the answer boxes or something like that. But that's the yeah, that's what that particular vector is doing.
Okay, and then yeah, this was the I was kind of confused on the part 5 because I got that right, got this one right.
Yeah, so that'll help kind of clear up vector C. Let me see vector C.
I pretty much got the tail wrong. Yeah, the tail wrong. Vector C,
yeah. Because C is starting from they give you the half value for Z and then 0 in X and Y.
Okay.
Is what that one's doing.
Well, that's what I was gonna ask.
That's what that should be, because it should be half and C the way they've given that. But what it might be is it might be they're saying it's 1 in, they might be saying it's 1 in Z. You'll have to take a little bit closer look at it. They might be saying it's 1 in Z, but half in, because that actually might be on the plane of x equals 1. So it might be actually half in y, 1 in x, and 1 in z from where that point is. Because if you zoom in real close, you're going to see that it actually isn't touching the z-axis. So
Oh,
it's
okay.
touching that front face. And that's the little stuff that you have to pay attention to.
Okay. Okay, I see. That's really
So tricky, but it's
yeah.
that way for a reason, so that when you go to the test, you're not going to be thrown for a loop.
So then yeah, it'd be if I understood that correct, it would be, what is that, x1? For the tail, it would be 1 in x, y would be half of y, and then z
Then
would be
z
1
would
as
be
well.
correct.
Okay. Okay. That's really
Yeah.
annoying. What else?
Yeah.
And
That's what's
then I spoke to you about the last homework with the decimal problems, like where it's like it wants me to add 10 decimals when I'm only
Yeah.
adding 2, 3. So what I'm gonna do is I'm gonna just, because obviously I've had this problem with this homework too. Like for question 2 and 4, it wants me to add a whole bunch of decimals when I'm,
Yeah.
you get what I'm saying. I'm gonna just
Yeah.
message you on Halo if that's okay.
Yeah, that'll be fine. I'll try and follow up from there.
Okay. And then I did hear that you mentioned the exam was open note.
Yeah.
But how much open note? Like, because I know, the math and the concepts and stuff like that.
Right. The notes that you guys have taken from class is what I'm referring to there. I'm not necessarily referring to like handwritten step-by-step homework problems, but the more of those that you guys have down, the more that you've effectively studied to learn the material. So it matters less from my perspective.
Okay, so I'm assuming no laptops then.
So yeah, no, well, it's we are going to be bringing in laptops because it's going to be an online exam. So there will be an announcement kind of clarifying what you guys need. So it is going to be online, but it's going to be set up where it's going to be in a testing window and all kinds of stuff. So it's going to be designed to be used with handwritten notes primarily.
Okay, that's fine. The only now, I'm assuming, will we have a lockdown browser or no? Because my camera doesn't work. So
It will be, yeah, it will be in, it will have its own browser locks and things. There's limitations to what I can do there, but it will be a fairly locked down browser from that perspective.
Okay. Okay, yeah, because my camera's like it's literally give or take, it works. And then
Yeah.
I've noticed sometimes it just like turns off. So
Yeah, the laptop cameras are all awful.
yeah, I just wanted to clarify. You don't have, I know other people offer office hours, but you don't have any, like, I don't know, even if it's like 30 minutes
I
particular
don't
day.
have any windows available right now. And um, the reasoning for that is because of the way that GCU structures the contracts for adjunct instructors. They don't include office hours. They want absolutely minimum work done to be able to get students through the class, is the way that they have structured it. So that's a thing that frustrates students, and some adjuncts will try and find some office hours. I just don't have any time availability for it.
Okay. Yeah, because I do have other questions for homework, but I'll try to figure it out. And if I can't, worst case scenario, I'll just shoot you a message if that's okay.
Yeah, that'll be fine.
Okay. All right, then. Thank you so much.
Absolutely. Take care.
You too.
So with accommodations, how's that going to work? I have really bad test anxiety.
Mm-hmm.
So how would that work?
That's a thing that you can physically go to the testing center. Because it's going to be online, I have to set up a copy of that for the students that need accommodations. I have to put those into a separate group, so you'll have a separate link from others that will be specific to the folks with accommodations, because they basically effectively give most everybody the same exact accommodations across the board, even though they will talk to you as if they're unique to every individual. They kind of have a blanket policy. So you can take it from the testing center physically. We just have to make sure they know that you are coming for Wednesday's class.
Yeah.
The length of time will be appropriately rescaled, and that's what we can do.
Awesome. Okay. Yeah, they have a big issue with electronics. So
Okay. They, unfortunately, that part I can't do much about because of the nature of the way this class is run. So we'll do what we can there.
okay.
Okay.
Do you want me to send you a message letting you know or reminding you?
Yeah, you can send a message, and I'm gonna have to get them back a list of people to talk to, or a list of people that may be showing up at the testing center. Some of them may take it from class, I'm not sure.
Okay.
But the additional time is why it'd be better to take it in the testing center, very likely.
Yeah. So it's next Wednesday, same time as class?
Yeah.
Okay.
Yeah, it's the same time as class.
So it's going to be over chapter 1 through 3. So like sorry. So the lecture notes, like in Wiley, is that a good?
That's a good reference point to study from, definitely, because that's going to cover a lot of the key concepts.
Okay. So like homework and then the lecture, like the PDF lecture notes from Wiley.
Yeah. Yeah, those will be good resources for you as reference points for sure.
Okay. Thank you very much. I have PTSD and like I freak out when I'm like in a large classroom, and I don't do well on tests.
Yeah,
At all.
It's a thing that unfortunately we have to do in order to assess things.
Yeah.
And there's ways that we could make adjustments to the class, but that's decisions all above my pay grade. So
Yeah, of course. Okay, I'll send you a message as a reminder, letting you know.
Okay. That'll
Thank
work.
you very much. And then the homework 4 is still due this Sunday.
Yeah, I'm trying to get that adjusted today so that it's moved back, so we have some more time on it.
Okay. Thank you very much.
All right. Take care.
You too. Thank you. Bye.
Have a good weekend. Bye-bye.
You as well. Bye.